Now, if we look at this example and we look at set B right here, any guesses what the cardinality of set B might be? So the cardinality of set B actually turns out to be 4, and that's one that we looked at last time, and we actually talked about that number 4. And what did we say? We said, hey, the reason that there's only 4 elements is you've got the element of just the 1, the element of just the 2, the element of just the 7, which were the easy ones, and then this whole guy that itself is a set. So the A and the 3 together is still just the one element of that set B. Now, any guesses what the cardinality of the empty set is? And I'll go ahead and write in here the other way of writing the empty set. Ooh, good guess. It does turn out that the cardinality of the empty set is 0, and that's because if you try to count up the number of elements inside of that empty set, notice there's nothing there. It turns out the empty set is absolutely the smallest set possible. Why? Because is there any set that could have less than 0 elements? The answer is actually no. It turns out one of the properties of cardinality, and I'll write this right up here for us, it turns out cardinality of any old set, smallest it could possibly be is 0, and then, well, it's got to be an integer. Because cardinality counts how many elements. So you're never allowed to have cardinality of 1/2. That makes no sense. How do you have half of an element? Okay. But yeah, so cardinality of the empty set is 0. It turns out this is the only set that has cardinality 0. So if you were told something like, hey, I have some set, I don't know what elements are in this set, but it has cardinality 0, you say, well, I know what elements are in that set. None, because cardinality 0. Now, last set here is the set of integers. Any guesses what the cardinality of the set of integers might be? Ooh, not 0. So 0 would mean there's no elements. Yep, it does turn out that this one has cardinality infinity, or what's otherwise known as an infinite set. So what people will often say is, because it's kind of it's not really non-standard, but people don't like to say equals infinity, because infinity is a concept as opposed to an actual real number. What people will often say is, hey, this is an infinite set, meaning you have infinitely many numbers. Slightly different part of speech. But if you need to put it in symbolic form, this would legitimately just be, hey, cardinality is infinity. Okay. It all means the same sort of thing. Why? You keep going, you could start writing down your integers and never get to the end. But that's it. In terms of cardinality, don't overthink it. It's literally just counting up how many elements you actually physically have in a set. In our class, we're going to focus mainly on finite sets. So this would be where you can physically get to what that real number is, what that integer number is. But we'll definitely be looking at some infinite sets as well. Most commonly would be set of integers, although we'll look at other ones too. Now, before we go on to the next example, let me throw an example at you guys. So let me go ahead and share this because we found that there were issues yesterday with me trying to do it inside of PowerPoint. So, can you guys see the second screen? Excellent. So that second screen is going back to Poll Everywhere like what we did last time. So it's the same URL if you're going through an internet browser. If you've got it set up on a phone or a tablet on an app, it's the same one that you just go to that same app you already have set up. It's only got 2 questions here. So the question on this one actually is dealing with the empty set. And I'm not going to read them out because if I read these guys out, it'll give away the answer. But the question here is, what do you guys think? Do you think that these 3 ways of dealing with the empty set, are they all the same? Huh? Don't overthink it. The first equals is true because that's this is writing it out as a set, and that's the symbolic form. So I'll give you a little bit of time to think about that. I see a couple of you have already started answering, actually more than a couple of you. There's only two possibilities. It's either true, and the thing you're looking at is this last equals right here. Do we think that last equals actually works? And it looks like all of you except for, ooh, excellent. All of you actually answered. And it should be set up so you can only answer one time. So let's see what you guys think. That's awesome. I have never had it that evenly split. Good job, guys. All right, so half of you are right and half of you are not right, okay? So let's go and look at, I'm going to keep this one up. We're going to come back to it, okay? So I'm going to move over here back to the PowerPoint slides and look at another example. So this set, I went ahead and tried to name it something that we haven't named before. I used S up at the top, and I just threw a bunch of, well, I don't want to say gibberish, but all sorts of different things in it. So this set, S is 3, it's E, it's the symbol for the empty set, it's 5, it's curly brace 7, comma, plus symbol, and curly brace, comma, 0. And what we want to do is we would like to figure out which of those guys, all dealing with the empty set. So very, very similar to the question that I just asked you. I'm going to go ahead and stop sharing this so the screen is bigger for you guys. We want to see which of these might be true. So what do you guys think? Any guesses on this first one right here? Does it look like the empty set is an element of that set S? Yeah, and how you can tell that is it's visibly, you can spot it. It's right there. So that one, totally true. What do you guys think about this second one? Do you think the empty set may be a subset of the set S? That one's a little bit trickier, but not much tricky. Ooh, I have guesses for both true and false. It does turn out that it is true, and the reason it's true is the empty set is a subset of, fill in your blank, any set you want. So S is some set, which means automatically your empty set is a subset. So that means this guy right here, the only way that that condition would be false is if S was not a set. And in our case, S is a set because we've got these curly braces right here at the beginning and the end. Now, the ones that are actually legitimately a little bit tricky. Okay. What do you guys think about this third option? It says you've got curly brace, symbol for empty set, and curly brace is an element of S. What do you guys think? Is that true? So I've got one guess. And you guys are correct. So that guy is going to be false. And so what I did is I went ahead and I wrote it down like what we did last time, which put the slash through that symbol for the element of. Okay? Now, why is that false? Up here, if that mess, if those symbols were actually an element of S, you would need the curly braces around the empty set symbol right there. Okay? So that would be the key thing of what's missing, no curly braces around the empty set. So that means this guy, not an element of set S. Now, last one does the exact same thing, except it switches out the element symbol with a subset symbol. Did that fix the issue? So what do you guys think? That last statement, does it look like it's true or false symbolically? Well, I do have guesses for both. It does turn out that this one is going to be true. Anybody have a guess why? Because I know that went counterintuitive to people. What would be the giveaway? How would you be able to tell that that is a true statement? How would we know that curly brace, empty set, closed curly brace really is a subset of S? This one here is probably the most trick question of all four of them. It's not really a trick, it's just, it feels weird. Anybody have a guess why that's true? Or why that would work? All right, I'm seeing no guess. So here's the way it goes. When you're dealing with a subset, so any subset, now I'll put this over to the side up here. So any subset of S can be built in the following way. Okay? You start off and you do curly braces, Y to make it a set, and then you pick any of the elements you want from over there. Now, if we were trying to check to see if this guy, where it's curly brace, empty set, close curly brace is a subset of S, what we would need to find is we would need to find that the empty set is an element of S. So what did we say up here at 1? We said the empty set is an element of S. So that means we can totally grab this empty set and throw it in here. We could have built a different subset where we threw in the 3 or we threw in a 3 and an E. Same process. But in this particular case, because the empty set itself was one of the elements, as soon as you put the extra set of curly braces around it, that converts it from an element to a subset. Okay? So these, the first and the last one right here, go hand in hand. Clearer, kind of better. Kind of makes sense. Yes. So the question here is what happens if you did something else? Suppose you pulled in an E. That's totally fine. That would also be a subset of S. You could also do something crazy. You could throw in a 5. You could throw in the empty set. You could even throw in that weird set that has the 7 and the plus. That whole mess would also be a subset of S. So it's the same procedure. It doesn't matter which one of these elements or combination of those elements you put between the curly brace. When you do that type of procedure, you'll build some subset of your original set, in this case S. And one of the very next things that we're going to do is we're going to look at how would you, actually the very next thing we're going to do, we're going to look at how do you build or how do you get to all the possible subsets. So that, we're going to get to that in just a second. We're not going to do it for this one because there's tons and tons. For this one, there's 64 different subsets. So we're not going to write out all of those guys. Okay? All right, so this here is the weird things that can go with the empty set. So let's go back to the question that we had asked before we got to this last example. So here's what we know. We know the empty set and then curly braces with nothing between them. These, same thing, just two different ways of writing the same thing. So the question, of course, is, are those two guys the same thing? And after the example we just did, what do you guys think? Is this last guy right here equal to or exactly the same thing as these guys over here? Probably the easier way to ask that question is as follows. We already found the cardinality of the empty set, written either way you want, is 0. Anybody have a guess on what the cardinality of that last symbol or that last set would be? This is a sneaky trick. Yes. It turns out the cardinality of this last guy is 1, and that is totally because you've got that one object, the empty set, between the curly braces. Now, why would I have bumped this to cardinality? One reason, we've just talked about cardinality, but really the main reason here is if you have two sets and they have a different cardinality, notice the 0 and the 1 are not the same integer. If they have a different cardinality, what does that tell you about the two sets? Could they ever be equal? Yes, I mean, correct. So these guys here, if you have different cardinality, so here's the property. If the cardinality of set A and set B are different, that means there's at least one element in either set B or set A, I don't know which one, that's not in the other set. And that would mean, then, there's no possible way that these two sets are equal. Same, if the two sets aren't equal, they could actually still have the same cardinality. And the example of that goes as follows. Maybe A is 1, 2. Maybe B is 3, 4. So in this case, those two guys are not equal, but their cardinality, they still both have 2 elements. Okay? So if you get that 2 sets are not equal, there's no guarantee that their cardinalities are different. But if their cardinalities are legitimately different, automatically there's no possible way ever for the 2 sets to be equal. Okay? So that's a nice little trick of quickly telling if your sets are equal or not equal. It's also a quick way to check to see if you already know your one of your sets is a subset. Like for example, this guy right here, we know that the set that contains just the element E is a subset of S. This guy has cardinality 1. Set S has cardinality what? 1, 2, 3, 4, 5, 6. It's cardinality 6. So that would actually mean that this guy is a proper subset. Why? Because it legitimately has fewer elements than the set S. So there's a lot of things that you can do with cardinality. I'm not going to ask you to do all of those different things, but it's ways to get more information about your sets. Questions? Make sense? Kind of? Feeling okay-ish? All right. In that case, let us move on to the next thing, and the next thing is properly building a new set. Okay? So what we want to do is we're given some set A, or whatever it's actually named. I'm going to call it A for the purposes of this definition. And we want to build a set associated with A, and this set is the power set. So if you talk about the power set of set A, this is a specific new set that was built from just the set A. And here's how it's defined. It's defined as a new set. Oh, just a second. Cardinality of a set. You speaking of this guy right here. So you just write 0. That's perfectly fine. So the question was about writing the cardinality of the empty set. This would be the only set where you just write the integer 0. All the other times it would be like integer 1, integer 2, integer 3, or if it's an infinite set, it's perfectly fine to write the infinity symbol. Although if you ever have to type it, I would type out the word either INF, as several of you did in the chat, or infinity, just because it's difficult to put the symbol up there. All right, so power set, this is defined to be the set of all subsets of A. So each element in your power set is itself going to be a set. So it's a set built of more sets. And we'll see an example, actually several examples here in just a second. There are 2 different symbols associated with the power set. This first one right here, I couldn't actually get it to type correctly. That 2 should be like a stylized Gothic 2 where there's no curved lines. It's all sort of jagged, more like this. I can't write it either. It's stylized is what it's trying to be. This one here is the official way of writing the power set, but it has a tendency to really mess with people's heads. So a lot of times, and actually a lot of textbooks, will instead use this symbol right here, where they have sort of a stylized or script-looking capital P, P here indicating power set. In both of these 2 symbolic ways of representing the power set of A, notice the set A is actually part of the symbol. So here the A is in the exponent. Here the A is inside the parentheses, so this one is very much function notation. Plug in the set that you care about, get back its power set. Okay? I don't care which of these 2 symbols you use. When I write up things, I will typically say find the power set of A, and I'll often give you both symbols. So if you just focus on one versus the other, totally fine. If you're reading through your textbook, your author only uses this first symbol right here. And if you look online, you'll find both of them. Now, it is easiest to figure out what's going on if we actually look at an example. Okay? And what I would recommend doing is anytime that you're trying to determine a power set or you're trying to build a power set of some given set, you actually do it by way of cardinality. Okay? And this is one of the reasons we made sure to do cardinality first. So if you want to find a subset of this given set A, notice you only have two elements that we're dealing with. You can only choose for your subset the element A or the element B, or both or neither. Okay? So if you build this out, if we look at all of the subsets of A of cardinality 0, don't overthink it. Any guesses which one or ones we would grab with cardinality 0? I stopped myself from giving away the answer there. So cardinality 0, there's exactly one set among all of the possible infinitely many sets there ever are. It is the empty set. Okay? So that's the only one with cardinality 0. It does turn out, if you're building a power set, all power sets include the empty set. So you start off with this one always. Now, then we've exhausted all the possibilities of subsets with cardinality 0. So if we do this strategically, next we would look at subsets with cardinality 1. Okay? Now, if you look at subsets with cardinality 1, any guesses how many possibilities there are? Or if you prefer listing them out. I was trying to get something that was easier to type when I said how many. So in terms of your subsets with cardinality 1, there's exactly two of them. You can either grab just the element 1 or you can grab just the element 2. The thing to remember about power set is make sure you put all of these as proper sets, or set notation is done correctly. Wow, that wasn't correct English-wise. Let's try again. Your symbols are correct to make it a set. So when you grab the 1 elements, we'll make sure we put our curly braces around. And at this point, there's only 2 elements that exhaust all the possibilities of subsets of cardinality 1. Now, next guy, subsets with cardinality 2. This means you have to have 2 elements. So any guesses what set this guy would be, or how many sets would have cardinality 2? Subsets with cardinality 2, excuse me. Yeah, it is only that full set A, and I'm not going to lie, I sometimes am very lazy, oh, let's face it, often very lazy, and just write the name of the original set. So here's what happens with your subsets. So suppose, let me make sure I'm not going to block anything that's about to fly in. Suppose you have some subset, so subsets, and we're going to call this guy, oh, I don't know, how about H? I was dealing with H's before this class, and that's a subset of our set A. In that case, notice what we just did when we built our power set. That was all the subsets of A. The cardinality of any subset, well, it could be the empty set, so it could be all the way down there at 0. But the largest it's going to be is the same as the original set. So this would be the cardinality of A. And that's a way to check to make sure you've built your right subsets. If you've built a subset and it happens to have 3 elements with this example, you did something completely and crazily wrong. Okay? And that's it for power sets. Power sets are literally just find all your subsets of a given set. Now, finding the cardinality of the power set is as simple as counting up all of the elements, which are all of the subsets of your set A. Okay? So in our particular case, if we take the cardinality of our power set, and I went ahead and used the notation with the 2's here, you could also replace that out with your P of A. In our case, we had 4. So empty set, the individual guys, and then the full set. So that's a total of 4. And any guesses why I would rewrite that as 2 raised to the 2nd power? Anybody spot something interesting about that exponent? The 4, I just counted. So it's this guy, empty set, the set of just A, set of just B, and the set of both A and B. The weird thing about counting cardinality of a power set is, for many people, it does feel very different than cardinality of other sets, but it's the same thing. You're just counting the elements, except now all of your elements are sets, which is, ooh, close. So I think you might be onto something there. The well, the rest of everything flew in. So yeah, in the exponent right here is the cardinality of the original set, and it turns out that that's true of any power set that you build. So power set of anybody, count up the cardinality of your original set. In our case, the cardinality was 2 of the original set, and that would tell us if we plugged it into this little notion, it'll be 2 raised to whatever the cardinality is of this particular guy. So what will happen, here it is right up here, you'll get, it'll tell you exactly how many subsets you're going to be looking for. Now sometimes all you care about is how many subsets do we have, and you don't care about listing them. Sometimes you're actually listing them out. So if you need to list out everybody, having that formula where it's 2 raised to the cardinality of whatever your original set is, means you're less likely to miss things. Or if you get where there's 3 of them, you know there's 1 missing, you got to go find it. Just as a heads up, this symbol here, that's not the integer 2, that's that stylized 2 that we talked about before. It's sort of like, if you will, a picture 2. Down here, this is properly the integer 2, and you really would do the math where you have the 2 raised to the 2 in this example, gives you back 4. So let us do another example of that guy. And if we do one more example of this guy, in this case, I went ahead and put it not in terms of A's and B's, but in terms of integers. So here, 1, 2, 3. Went ahead and called it something different too. Okay? So suppose we want to do the exact same thing. We want to find the power set of some set, and in this case, I called it B just to hopefully not confuse people with the same name as the previous example. Okay? So to actually find this power set, same thing occurs. Symbolically, you can write this as either script P, the power set of P with that scripty P, or you can write it with, I couldn't get a stylized 2, a Gothic sort of looking 2 right here, but I did the best I could, which is looked like a normal integer 2, and then put the name of whatever set you started with up in the exponent. This here is not, this is just a symbol. It's like the name of it, okay? Just like f of p is the name, would be, f of b, excuse me, would be the, I can't speak today, p of b. B was a bad choice for a name. P of b out here. Okay? Now, if we want to go ahead and build this thing, we can do the same strategy as before. We can start off and say, hey, we want to go ahead and find all of our subsets of B with cardinality 0. And who did we say was going to be a subset of B with cardinality 0? Anybody remember that one? Yep, so just the empty set. Then we'll look at subsets with cardinality 1. So in this case, any guesses what those subsets with cardinality 1 would be? Yep, you could pick either 1, you could pick 2, you could pick 3. So if we're trying to find all of the subsets with cardinality 1, we would actually go ahead and grab all 3 of them. So 3 different possibilities there. Now, the next thing down would be dealing with subsets of B with cardinality 2. Now, in our last example, our original set that we started with only had 2 elements, so we were done at this stage. Now our set has 3 elements, so we're actually going to, well, have more than one option here. So any guesses what some of the subsets with cardinality 2 might be? Yep, and you actually got them all. So here, one of the ways to think about it is what set you're missing. So here, not set, what element from set B you're missing. So here, I didn't include 3. Here, didn't include 2. Here, didn't include 1. And that's it. Now, if the original building set is bigger than 3, it's a little bit more complicated, but it's still the same sort of idea. Now, in this case, we can actually go another stage and look at all the subsets with cardinality 3, and any guesses what the subsets with cardinality 3 would be here? Yep, and either way, totally fine. You can either write it as the quick and lazy way and just saying that this is set B because we have its name already, or actually list it all out and it doesn't matter what you do. Okay? And then notice if we actually count up the cardinality of this guy, if we physically count all of those subsets, How many do we get? Now, if we look to see if our formula actually still holds water, in this case where we now have a larger set that we started with, what was our formula? Our formula had said 2 raised to the cardinality of whatever b was. The cardinality of b is 3, 2 to the 3 is 8, so yep, that formula still works in this situation. It actually turns out it'll work all the time. It comes from the fact here of you've got all of your possibilities. You can either include 1 or not, that's 2 possibilities. Include 2 or not, 2 possibilities. Include 3 or not, 2 possibilities. So it's in terms of total possibilities, 2 times 2 times 2 is where that formula actually comes from. Later on in the course, we'll talk about how you deal with counting total number of things, and we'll actually see where that formula came from a little bit more with those properties. So questions make sense, kind of feeling okay, just a little bit in terms of the power set. Awesome. Not going to lie, power sets do have a tendency to mess with people's heads, and it's not because you can't do it. It's just because, 1, you forget to write all the curly braces, so minor issue there. So it might be something where you put a sticky note. Remember to put the curly braces for my subsets. And the other thing that causes people trouble is if you don't do this sort of structured attack on finding all of your subsets in some sort of order, it's very, very easy to miss a subset, because they can get crazy complicated very quickly. All right, so that deals with power set. The next thing, and I am assuming that most of you have dealt with Venn diagrams, and this is only because every so often I'd love to give you guys a picture illustration. When we're dealing with sets, we can totally illustrate sets with Venn diagrams. Now, just to remind ourselves what all the symbols mean here, when you're dealing with sets, you don't always have a universal set, but let's face it, most of the time, even if you're not told what it is, implicitly there's some sort of universal set. Like, for example, maybe it's all integers, or all letters, or all integers and all letters together. Okay? So this is wherever you're pulling the elements of your set from when you build your set. Okay? And that's what the rectangular box represents. Now, in terms of the bubbles, the circles represent your sets. So set A would be this one that's shaded in that sort of weird orange dirt colored, brownish color. And set B here, this sort of grayish bluish color. Now notice set B here, this bubble is completely inside of set A. So that tells you that set B is a subset of A. And the individual dots here represent individual elements. So this dot right here that has an X tells you element X is inside of set A, but not inside of set B. And that's why I can go ahead and say a proper subset. B is a proper subset of A. Okay. So here, X is inside of A, X is not inside of B. We just talked about that. That's where you get the proper subset, or the two sets are not equal to each other. And this here, we're going to define this symbol in just a second, but what this says is X is inside of A, but not inside of B. And Y here is not inside of either. And that's it for Venn diagrams. It's literally sort of bubbles for sets. And we're not going to do anything more complicated than what we just said right here. Now, in terms of operations on sets, I am assuming that you guys have done some of these operations, but I'm going to go over anything just in case it's either been a while or you haven't done it before. Okay. So the first operation that we've got is union, also read as OR. So in terms of symbols, it looks like this sort of U-shaped. Don't actually put a vertical bar here like you normally would for a proper U. And this is defined as all of the elements that you grab from your set A as well as your set B. And specifically, it's read as OR. But what's really going on, there should be a picture that flies in. Apparently, the picture is going to come in after both definitions. It's literally, sort of picture this as you have a bag that's everything in set A. You have a bag that contains everything in set B. And you dump both the bags out and mix them all together. So that's sort of the idea. Now this complicated notation down here, this part on the right-hand side just says I have set, the first set union with the second set, union with, keep going all the way to n sets. If you have n different sets, you'd actually know what your n is typically, and you union more than 2 sets together. This here is simply the shorthand notation that says the exact same thing. It says I'm looking here at set A, subscript with I. This index here starts at 1, and it goes up by way of an integer until you get to the last index, which would stop at n here. And the operation between them is the union. If you've ever taken Calc 2, which is typically relatively high percentage of people if you're in this class, this is similar to the sigma notation that they had with series. The only difference is instead of a sigma where you add things together, we're now unioning things together. If you haven't dealt with that notation, don't worry about it. We're not going to use it. Okay. The other common operation that typically goes hand in hand is intersection. This guy's also read as properly and. So here, this guy looks like an N or an upside down union symbol, and this is the common elements that are in both set A and in set B. In terms of the Venn diagram, this will be the overlap, and you can also do the fancy notation there too. There's the pictures. They're timed to come in at the right moment, and the right moment obviously was not put in here correctly. Sorry about that, guys. So here the union is literally this part right here. Everything in A, everything in B, and you only want one copy right here between the two. So remember, sets are your disjoint elements. So when you dump set A and set B together, any duplicated guys get rid of the extra copy. In terms of intersection, we only want those duplicated guys, still only one copy, but you're only going to grab the elements that are in both of the 2 sets. Okay? And that's it in terms of unions and intersections. Questions before I go to the next operation? All right. So actually, before we go to the next operation, I went ahead and threw it to you guys to make sure we're all comfortable with everything. Let me pull this up so you guys can see it just fine too and activate it. Is the screen yellow again? Yep. All right. So I just shared a second screen with you, and I'm going to get this one so it's not yellow, hopefully. There we go. So you should be able to see now this question in potentially 2 places. Apparently. Okay, that's weird. Oh, it just looks like I reversed the thing. So let's actually do it reversed up here too. There we go. All right, so this one here has 2 sets, and there's going to be 2 questions. One of them asks you about union, and the other one asks you about intersection. So set A, and I'm just going to read them out for you guys. Set A is 1, 2, E, and X. I didn't put anything weird like we've been doing with sets that have sets inside of sets. And the second set we have is B, also 4 elements, and these elements are 1, A, E, and Y. And what we would like to do is we'd like to find the union of these 2 sets. Okay? And there's a bunch of different choices right here. I'm going to let you guys take a moment, see if you can figure out which one you like or don't like. And it looks like most of you have answers at this point in time. Awesome. All right, so let's see. Ooh, I love it. So we have all sorts of answers involved here, so let's go ahead and figure out which one of these answers work. I'm going to go ahead and get rid of the second screen now that you guys have worked through. Oh, 14. How did we get 14? I'm not going to overthink that. Oh, I bet I let you guys pick multiple things, didn't I? That's probably what's going on. I was thinking one answer. All right, either way, I'm going to hide the second screen for you guys right here. That way this one comes up bigger. All right, so we had lots of different answers. There's a couple of answers that we can immediately exclude. Did anybody figure out which answers you could immediately exclude? Don't try typing them. There's something in common to the answer choices. So if you don't have brackets, it's not a set, and both union and intersection are defined to be new sets. So I'm going to go down here in these microscopic little guys that are hard to see. I'm going to go ahead and circle it. So these guys right here, all three of these guys don't have brackets, which means they're not sets. Okay? They're a list of elements, and there's no problem with being a list of elements. But in terms of being the new set, which is the union, they're not going to be it because they're not sets. And that then eliminates this down to the answers that actually do have brackets. Now, once you have the answers that do have brackets, there's one of these answer choices that's also something you can relatively easily exclude. And feel free to just give me the position on this one, like first, second, third. Anybody have a guess of which of the three guys with brackets, so the second answer, the fourth answer, or the sixth answer, can also be easily excluded? You guys are saying fifth answer, but we already crossed off the fifth answer. Do you mean the fourth or the sixth? Okay, yes. So this one right here, that last guy, that sixth answer, we can also go ahead and cross him off. What do you guys? Sorry, I had a momentary counting issue. Anybody spot why we can automatically exclude this last guy? Yes, you guys already told me. It repeats, and it repeats in several places. I'm going to go ahead and underline right here with the ones repeat. So technically speaking, if you were writing this out on your own for an answer, this would be a first draft. You throw everything together, totally fine. But then you go to finish your answer and cross off all those duplicated items or duplicated elements. Okay. So this now gets us two possibilities. We've got the possibility of the set 2a, x, and y, and we also have the possibility of 1, 2, a, e, x, and y. I did not mean to cover up the y when I did scribbly work. So which do you guys think? Second answer or fourth answer for the union? So it does turn out that our union is, in fact, that guy right down there. So let me write it a little bit bigger for us. What do? You can throw in everything from set A. Then you don't need to throw in the duplicated items from set B. 1 and E are already in the set we're building. You only throw in the A and the Y at the end. And yes, I realize the order of what I just wrote is different than what was typed up right here. What was typed up was just alphabetized and putting the numbers first. The order that you write the elements in your set doesn't matter, so you can make it as pretty or not pretty as you want. Okay? Now, doing the exact same thing, what happens if you were now asked to find the intersection? Okay? So I went ahead and activated the next question, and I'll throw it up here as well. Same two sets, but now you're asked about the intersection. Choices, I made the choices a little bit different, and they're definitely easier to see on the PowerPoint screen. And just remember, there's some guys that are very easy to exclude. I would definitely recommend excluding them first while you're thinking about this. So it looks like most of you have got answers. The key thing here is remembering the definition of intersection. It's not throwing everything together. It's only select some of the elements. All right, I'm going to go ahead and hide the second screen just so that when I scribble on the PowerPoint slide here, it'll be bigger so you guys can see it up the way it's here. But that little question is still active, so if you can still do selections if you haven't finished yet for the two of you who don't have answers yet. All right, so if we're looking at the same two sets, so A is still 1, 2, EX, B is still 1A, EY, no worries there. If you wanted to find the intersection, what are the possibilities here that we can easily exclude? So just like last time, we had a couple of options that you could just easily cross off. Did we have any easily excludable options here as well? Feel free to get. Yep, you guys are right. It's the ones without the curly braces again. So actually the first three guys we can go ahead and exclude because they're not going to be sets. And just like union, intersection is defined as a set. Okay? Now, that gives us three possibilities for our intersection. So we've got a couple of different things we could do. One of them is this last guy, which is 2A, X, and Y. What do you guys think? Is that guy an intersection? Correct. So this last one is not an intersection. Why? Because the thing that you need for an intersection is what? You needed it to be all of the elements that were in both of the two sets A and B. Is 2 in both the sets A and B? Nope, it's in A, but it's not in B. These guys actually turn out to be the elements that were in exactly one of the two sets, but not both. Ooh, it's actually not a union. This one here is what's known as a symmetric difference, and we'll get to it in just a second. So this one here, even though it's a set, it didn't work out so well. Now, the last two, if you look at both of the elements, either the 1 or both the 1 and the E, those guys are elements that are in common of both A and B. So the question is, which one of them is defined to be the intersection? What do you guys think? That fourth option or that fifth option? Yes. So this one here is going to be defined to be your intersection, and that is because the intersection is not just any old set where you grab the elements that are in common to both A and B. That deals with this one too, is fine. But it's you take all of the elements that are in common of both A and B. Subtle difference, but that makes it where you have exactly one answer for your intersection. And that's it in terms of intersections and unions. And if you guys want to use Venn diagrams and throw all of your elements into the Venn diagram picture and do it, totally fine. If you just read it off the sets, totally fine. There's definitely different ways of finding your intersections and unions. Okay? All right, so the next two operations that we have, well, that didn't work out so well. Let's put it here. I'm trying to make it fly in for you guys. There we go. Oh well, it didn't happen anyway. All right, so what we've got here is complement, and then we're going to look at set subtraction. So complement also, looking red is not. So it's got a bunch of different symbols that people like to use. This one here where you have a bar over top is a really, really common way of doing it. And what it says is the complement of A is all of the elements in your universal set. So this is pretty much the one operation where you have to know what's your universal set. It's everybody in your universal set that's not in the set A. These are all the elements that are not in set A. Now, other common notations that you'll see are the set A, and then up in the exponent, either an uppercase or a lowercase c, C for complement. You also see C down front, and then A, so it looks like a function notation. That one is much less common. Most common are these two guys. In terms of a descriptor, this here is using the definition of set subtraction, which we'll talk about in just a second. It says all the elements of A, universal set, they're not in A. And in terms of the Venn diagram, it's the shaded space. So everybody not inside of set A. Don't overthink it. It's just the guy's not in A. Now, set subtraction, you don't actually do integer subtraction. Set subtraction is where you remove elements from the set. So it can be defined or written out in two basic ways. Set subtraction itself officially is A subtract B. So this is all the elements that are inside of A, but then you remove the ones that are in B. So you essentially take A and then get rid of the intersection of A and B. Okay? Now, and the other way of writing it is set subtraction is also exactly the same thing as the intersection of set A and the complement of B, so everything not in B. So that intersection would also be this shaded way. And some people prefer to think about it as this way. This just is more complicated to write. In terms of actually what you do when you're playing around with the sets themselves and the elements, this is you take A and you remove the intersection of A and B. And that's it for those guys. Now, before we jump into examples with these guys, let me go ahead and get us the last operations. The last operation is symmetric difference, and this one didn't come up nice when I tried to make the picture. So symmetric difference, it can be written one of two ways. The more common way of seeing it is with a little triangle between the two sets. And this is all of the elements that are in exactly one of the two sets. They're either in set A or they're in set B, but they're not in both. So notice it looks very much like a union, except you don't have the intersection right there. So it's called symmetric difference because this part right here, that sort of half moon shape over A, is A subtract B. Over here you have B subtract A, so the other sort of half moon shape. I'm not going to lie though, in terms of writing it like this way, it always feels like I'm going to mess up if writing the A or the B first. So the other way of writing it is this is the same thing as union, get rid of intersection. Okay, so that's the symmetric difference. And that's it for symmetric difference. And the last thing is a property, not an operation. And this is the property of having disjoint sets. Disjoint sets are when you have two different sets or more than two sets where there is no element in common. In terms of the Venn diagram, notice there's no overlap. And in terms of symbols or the definition, we've got the intersection of A and B equals the empty set. Okay? So this is a property, not an operation. Let us look at an example here. So I went ahead and threw in some funky symbols for this one. For our universal set, I said let's use the integers 1 through 5, the letters A through E, and throw in some funky symbols of this square with a dot in the middle, a star, and a triangle, just because. Okay. We then go ahead and say that set A is set 1, 2, E, and star. Set B is 1, A, E, and triangle. Again, just pulled some random guys from the universal set. Okay. So if we wanted to go ahead and find the complement of A, I went ahead and wrote out what set A was and put the complement symbol on there. What would be the procedure in terms of what we would want to do to find that complement? Don't overthink it. Anybody guessing a procedure we should do to find this complement? Not asking you to find the complement, just what the procedure would be. Yeah, that would be the best way to do it. Look at your universal set, cross off the parts in common, okay? So in this case, I'm actually going to do that, and I'm going to attempt to do it in a fly-in, is what I attempted to do. So here, I went ahead and just wrote out the universal set. In red or in bold here, I went ahead and highlighted the actual complements. So if you were doing this on your own piece of paper, cross off the 1, the 2, the E, and the star. Don't just make them red. Okay? Which means that the final answer would be after you remove those crossed off elements. So bam, those 4 guys. And that's it. That's all you do with complements. Don't overthink a compliment. Okay. Next example that I've got for us is what happens if we have set subtraction. So suppose we take set A and we want to subtract set B from it. Be careful, be careful, be careful. Set subtraction is probably one, it's not a complicated operation, but it's one of the ones where I see the most mistakes. Why? Because people are trying to legitimately subtract. So they try to actually subtract the 1 from 1 and get a 0. There's no 0 in the universal set. You can't write it down. Okay. So set subtraction goes as follows. You're going to remove all of the elements of B that are also in A. Okay? So I'm going to do the same sort of thing that we did with complement. I'm going to write out all of the elements of A, but highlight the ones that are also in set B. It was the 1 and the E. That's it. Both the 2 and the star are only in A. So A subtract B, or A set subtraction B, says cross off those elements that were in B. So your final answer here is some subset of A, and it will always be some subset of A. In this case, just the 2 and the star. Note, this is totally like saying find the complement of B where A is the universal set is another way of talking about it. And in math, we would say complement of B with respect to A. Questions make sense, kind of okay with a set subtraction. Okay. So last example on this page, and we'll have another example in just a second, is what happens if we wanted to find symmetric difference. So I'm going to go ahead and write out the formula that's union minus intersection. But remember, the official formula for symmetric difference is A subtract B, union B subtract A. And if you want to use that formula instead of what I'm about to do, that's totally fine too. Okay. So here, first thing is we need to figure out the union and the intersection. So the union of A and B is going to be both A and B dumped together in one set, but we won't write the duplicates. The intersection will be what are the elements in common. The intersection of A and B is what? It looks like 1, and it looks like E. The intersection will be 1 and E, and we won't write down the 1 and E twice over here. Okay. So 1 and E, and this is everything else. So from A, 1 to E and star. From B, 1, A, E, and triangle. Then we get rid of all the elements that were in the intersection. So doing the same procedure that we did in the last 2 examples, highlight the 1 and the E, or really if you're doing this yourself, just cross off the 1 and the E from the first part. And so our final answer is just the 2, the A, the star, and the triangle. Don't overthink this. You can totally jump straight to that final answer in your head if you walk through all of the elements in A and B and say, hey, is this element only in A and not in B? So for example, if you wanted to jump straight to this set right here, you say 1, nope, 1's in both of them. 2, yep, 2's only in A. I'm going to write it down right over here. E is in both of them. Don't write it down. Star, yep, star's only in A, so write down the star. 1, nope, we already excluded 1. A is only in B, so write down the A. E, nope, E's in both. Triangle, yep, triangle's only in B, so write it down. So that's another way that you can go ahead and jump straight to the answer. And that's it for symmetric difference. Okay. Questions? Make sense? Feeling okay so far? All right, seeing no questions, let us look at another example. The next example that I've got prepped up for us is totally not anything new. It's just what happens if you start combining the operations together. So for this one, our universal set, I was extra super lazy. I just did the integers 0 through 9, so all digits. And set A is just 0 through 4, super lazy. B, 0, 3, 6, 9, so the multiples of 3. C, 0 and 5, so multiples of 5. And D, random, 1, 7, 8, and 9. Okay. So 2 examples to look at. The first one is we want to look at the intersection of the complement of A and D. I totally read that wrong. The intersection of the complement of A and D. And then we want to set subtract from that the union of B, C, and D. And the other example is first we'll union up A, B, and C, take its complement, and intersect that with D. Okay? Order of operations, just like you would have had in some sort of algebra class or calculus class or wherever you've had it in the past, still apply. If you have parentheses, deal with the parentheses first. Okay? So just to do this logically, let's start over here on the left-hand side. So at this first stage, I'm just going to copy down the information. So let's actually go back a stage. So D, I'm just going to leave alone. But if we look at the complement of A, the complement of A will be everything that's not in A, but in the universal set. Notice A was picked nicely, 0 through 4. The complement of A will be just cross off 0 through 4, and we'll get 5 through 9 remaining. Now the union of B, C, and D, we're going to throw B, C, and D all together. So we're definitely going to have a 0, 3, 5 from C, 6, 9. Oh, we missed 1, 7, and 8, and 1 still need to be in there too. So all these numbers will be thrown in there together. Okay? The 1 here, the 0 from here, 3 from there, 5 from there, 6 from there, 7, 8, 9 from over here. And there are some duplicates as well. Now, at this stage, any guesses what the next operation is that we need to deal with? Should we deal with the set subtraction next, or should we deal with the intersection next? What do you guys think? So we need to deal with the stuff inside the parentheses first. So we'll want to deal with the intersection next. So D here was 1, 7, 8, and 9. So if we intersect D with the complement of A right here, that is going to simplify, or it'll condense down. Notice the only things in common are the 7, 8, and the 9. Okay? So we've got the 7, 8, 9, and then we'll set subtract all of that. Now here's the part where people all of a sudden their brain starts freezing on them. If we want to set subtract this set, which is much, much larger than this set right here, and I keep saying this and that set because there's no names for either of these guys, any guesses what the answer would be? Don't overthink this. It all goes back to the definition of set subtraction. Ooh, all the guesses so far are definitely overthinking it. Remember what set subtraction means. It means remove any elements from this second set from the first set. So your answer is going to be a subset of 7, 8, or 9. Does that change any guesses? Ooh, one of you got it. It turns out to be the empty set. Now, why? We're not actually doing real subtraction here. What we're doing is we're only removing anything that's from this set that's also in that set. Okay? So notice there are only, what? 0 is not in the first set, 1 not in the first set, 3 not in the first set, 5 not in the first set, 6 not in the first set. So these guys don't matter. They are extra information that we don't care about. Okay? Now 7 is in the first set, so we'll cross it off. 8 is in the first set, so we're going to remove it. 9 is in the first set, so we're going to remove it. And those meant to be full slashes, they turned out just to be tick marks. Sorry about that. So we removed all of the elements from that first set, which means there's nothing left, or we get the empty set. Okay? Notice that subtraction, it does not, if you are very precise with the definition, which just means I'm removing an element from a set, you'll be fine. But it definitely doesn't feel like that when you're first using it. You always feel like you want to actually do some sort of subtraction here. You're not actually doing subtraction on integers in any way, shape, or form. Set subtraction is just removing an element that we're no longer going to want in our set. Feel kind of okay, a little bit better? Makes sense why we got the empty set? You can't see it, but I'm crossing my fingers. Hopefully that means everybody's okay. I'm not seeing anything from you, so I'm hoping everything's okay. All right. If not, let me know when we'll come back to this one. But let us jump to this second example. And this second example, I'm not going to lie, the second example is a little bit easier. Ooh, there's a question. I knew there was going to be one somewhere. So we got rid of the 0 through 6, not because we needed to actually get rid of them. They were just extraneous information. It was information we weren't going to use. So the definition of set subtraction says if you are in this format of, and I'm going to use different letters from A through D. Let me say P, and Q. So suppose this second set here would be like Q, this first set here would be like P. What you do is you remove any elements in P that are also in Q. So in actuality, what you're doing is this. It's P, remove all of the elements that are in both P and Q. So by crossing off this 0, 1, 3, 5, 6, I chopped set Q down into Q intersect P. So it's only getting us down to the elements that we actually cared about. Once you get down to the elements you actually cared about, the set subtraction tells you to remove those elements from the set that we called P. Hopefully that makes a little bit more sense. I have found that people actually, it makes more sense to people if you actually write it this way, even though there's, in terms of the actual definition, that's not what math people will normally ever write. All right, awesome. If you guys have more questions about this, just shout them out and we'll come back to it. So if we go to our next example here we're only doing intersections, unions, and complements. So first thing that we need to do here is we need to find the union of A, B, and C. Now if we look at A, B, and C, notice A is 0 through 4. C is 0, we already have that in A, but C also gives us 5, so we're right now 0 through 5. Then we look at B. B has 0 and 3, we already have 0 through 5, so we got those two. But B also has 6, so now we're 0 through 6. And B also has a 9, so we're going to be 0 through 6 and then 9 for the union. I wanted to walk that out so this made sense when we flew it in. Then we need to take the complement of the union. And the nice thing about this union being so large, when you take the complement, it's going to be relatively small. Anybody got what the complement of the union of A, B, and C would equal? Yep, it would just be 7 and 8. So we're going to have 7 and 8 intersect D, and D right here is just 1, 7, 8, and 9. So if we do this intersection, any guesses what the final answer would be? Almost. It is going to include an 8, but it is also going to go ahead and include the 7 because 7 was also in D. And that's it. Notice both of these had some extreme answers. Down here at this last step, the intersection turned out to be one of the sets. Typically, it's smaller than one of the sets. And over here, we had another extreme case where we got down to the empty set. So these two are sort of extreme answers. Most of the time, you have somewhere in between where you have a couple of the elements that you've been dealing with your previous sets, but not all of them. But that's it for some of these more complicated examples of how you can throw the different operations together. All right, so the next thing that we've got and is the last big operation. It's something called the Cartesian product or the product set. Okay? And this guy here, in terms of how it goes, is you start off with two sets, and you can actually do this with more than two sets. And we're going to define the cross product of two sets as an ordered pair. If you have more than two sets, it wouldn't be an ordered pair, it'd be an ordered, say the number of sets you have. So if there's 3 sets, it'd be an ordered triple. If there's 4 sets, it'd be an ordered 4 tuples, what it's actually called, where you have 4 elements. What happens here, the key thing with a cross product or a Cartesian product is you've got all the elements from A would live in the first position, and that corresponds right here because A is written first, and all the elements of B are in the second position or written in the second position because set B is written in the second position. And that's it. Now, that being said, let's look at an example because it makes way more sense with an example. So suppose you have some set A, and I was super lazy, I just picked 1, 2, 3. And set B, E, and T. I was trying to be slightly fancy there. On purpose, I made the cardinality of these two sets different, in part so it's easy to write out, and in part so it's really obvious to see where the different elements are coming from. So if we want to go ahead and find this cross product, we can do this strategically. Now, you don't have to do it strategically, but I would recommend doing it strategically. The elements from set A are going to be in the first position of an ordered pair, so maybe we start with element 1 first. Okay? So here, if we start with element 1, we can put either element E in the second position or the element T in the second position. And since the cross product is all possibilities, you'd write down both the 2 ordered pairs. Now, if we did the same thing, but we started with number 2, or integer 2, as the first coordinate of our ordered pair. Any guesses what the second coordinate of our ordered pairs are when we start with a 2? In other words, 2 comma something. What should be in that something? So it would look exactly like the previous line, except instead of 1, you'd have a 2, so you'd have 2e and 2t. Now, in terms of writing it out yourself, make sure you have those parentheses. The parentheses are really important here. But I'm not worrying about it in terms of what you're typing in the chat, because let's face it, we just want to communicate there. All right, so are there any other objects in this cross product? What do you think? Any other objects in this set? Yep, it turns out there are a couple more, and these are the ones that are going to start with 3. So any guesses what the elements are that are going to start with 3? And they will look in the exact same format of the other guys here, 3e and 3t. And I went ahead and closed the curly brace here. Why? Because we've used up all of our elements from A, 1, 2, and 3, all of our elements from B, E, and T. And if we looked at the cardinality of this guy, this would be a cardinality of 6. Why 6? There's 6 ordered pairs. Okay? Now, you guys notice anything about that number 6 with respect to the cardinality of A and B? Yeah. So it does turn out the cardinality of A is 3, cardinality of B is 2, and it turns out that when you're writing out all the different possibilities of these ordered pairs that we can build, there is a property that says as long as the 2 sets A and B are finite sets, you can actually count up how many elements are in there, you will get that the cardinality of the cross product is exactly the same as the product of the cardinality of A and B. And yes, that's crazy to talk about. Okay. Now, we have an activity, and the activity talks about both cross products. It also talks about power sets. I think it's going to take longer than the couple minutes we have left in class. So what I'll do is I'll plan on that activity, us looking at it first thing tomorrow. And instead, let's finish off today with I'll show you some of the properties with unions and intersections, and then we will be done for today. Okay? And then we'll finish up sets at the beginning of next time. So here's some properties of sets that you can see. First thing is union and intersection is what are called commutative. Commutative simply means the order doesn't matter. So it doesn't matter if you write the set A or the set B first. I don't care if you remember this name whatsoever. This is just you dealing with unions and intersections in the future. Okay. The next thing is unions and intersections are also known as associative. Again, I don't care if you remember that term or not. Associative just means if you have 3 or more elements, it's defined as specifically on 3 elements, that if you have a binary operation, union and intersection are actually considered binary operations. Yes, I can. So binary operations are dealing with 2 things. So like addition is binary, you add 2 things together. But in reality, what happens, you're really going to deal with more sets than just 2 at a time. So associative says it doesn't matter whether you do those sets all together, whether you do you take the union of the second 2 first, and then throw in the third one, or you take the union of the first two first, and then throw in the third set. Okay. So that's associative. In other words, you can do what you always thought you could do. Distributive is a little bit different. So distributive is the interplay between both the union and the intersection. This is the same thing if you were in an algebra class where you'd have something like 2 times x plus y. You distribute the 2 on the x and the 2 on the y. So like this. I'm going to regret this in just a second. You can do the exact same thing with unions and intersections. Unions and intersections actually work the same way as multiplications and addition. So you'll see very similar type guys. Notice here, if we tie this into the union and the intersection, here if you have A intersect A union, when you distribute the A through, that intersection goes with the A. And then the symbol between the B and the C here splits it. And the same distributive property works if you flip-flop the union and the intersection. Oh no. I knew I was going to regret that eraser. Oh good. Whew. Oh good. And we'll pick a different color because the red was annoying me. All right, that's distributive. Idempotent, or I can never say it right. I put an extra D in there. We'll just go with it. Idempotent properties. This here is like saying x squared equals x. So if you union two sets together, turns out it's just the same set. If you intersect two sets together, it's still just the same set. Again, don't care if you remember the name or not. The next guys are some properties of complements. If you complement a set twice, don't overthink it. It's like a minus. You take a negative 2 times, it goes back to positive. So complement a set twice and you get back to the original. Now, if you union in a set with its complement, so here's the original set inside the bubble in this Venn diagram. The complement is outside. This is going to give you the entire universal set, and that's it. Or that's everything. But what happens if instead of union, you intersect? Well, it turns out if you intersect a set and its complement, notice the complement and its original have no overlap. That means you're actually going to get the empty set. And if you happen to complement an empty set, well, everything not in the empty set is everything, or the universal set. And vice versa, if you complement a universal set, you'll get, well, everything not in the universal set, which is nothing, because it's a universal set. Now, these next guys are specific to your universal set, and the empty set, it's a little bit of a lie. This also works if you just have subsets as well. So if you trade, anyway, I'll talk about that later. So if you have A union a universal set, the universal set is bigger, so you'll get the universal set. This is the same with subsets. A is a subset of something else. The union would be the bigger one. If you union any set with the universal set, it'll be that any set. Same deal if you have subsets. So here if you have A is a subset of something bigger, the intersection will be the smaller of the two sets. Same deal if you deal with empty set. So the union of A and an empty set, well, that would be A, the bigger set. If you intersect A and the empty set, that'll be the empty set, the smaller of the two sets. This only works because the relationship between A and the universal set, or A and the empty set, is in fact a subset relationship. So notice right here, this is the general case. If A is a subset of B, the intersection is the bigger set. I lie. The union is the bigger set. The intersection is the smaller set. And the last property that we have is De Morgan's law. If you've ever dealt with De Morgan's law before, this is the exact same thing. There's 2 of them, and it deals with the complement of a union or the intersection of a union. And specifically, De Morgan's law is when you union or intersect 2 things, although later on in class, we'll actually look to see how De Morgan's law can work if you have the union or intersection of more than 2 things. It turns out it works just fine. So I'm just going to go through the first one and use Venn diagrams to show you why this would be true, just to sort of that way you don't have to take it just on faith if this is true. Okay? So if you ever wanted to use Venn diagrams to show that some property of sets is true, here's how you would do it. So on the left-hand side, so this side here with the union, you do it in 2 steps. The first step is you grab the union. That's the same picture we had before. You shade in the union part. And the complement then is everything outside of the union. Then you grab to the complement. And that's it for the left-hand side. Totally fine. Now, if this property is true, we better get the exact same picture on the other side, or on the right-hand side. And I'm going to abbreviate that one as well. So on the right-hand side here, here's hoping there's no typos. We'll start off and we look at the complement of A. So the complement of A is everything in the universal set that's not A, so all that shaded region. Then we're also going to look at the complement of B. And notice here, because we want to deal with, can't find my cursor. Notice since we want to deal with, there it went. We want to deal with complements first and then intersections. You actually have 2 different pictures over here. Then you go ahead and intersect. When you intersect, you're going to sort of put these two pictures on top of each other and only save the shaded region that's in common. When I do this by hand, I'll often, when I put the two pictures together, like crosshatch one of them one direction and crosshatch the other one the other direction. That way you don't have to try to do all of it in your head. And when you do that, notice what happens. You're not allowed to have anything in A. You're not allowed to have anything in B. So the only thing that's going to be in common between A complement and B complement is going to be the shaded outside part. And there was a typo. I thought there was a typo. I'd forgotten to fix. So this would be the complement of A intersect the complement of B. And then you could say, hey, because we got the exact same picture for the two Venn diagrams that we created, this is an illustration or shows why that first De Morgan's law works. And you can do the exact same thing for the other De Morgan's law as well. But that takes us through all of our properties of sets. The only thing that we've got left to do is we've got that one activity to make sure you guys are comfortable with power sets and cross products. And I'll go ahead and take that same activity and just put it on for next class. We'll start off with it. And the only other thing that I had geared up for us to do in sets is talking about something called inclusion, exclusion, and that's dealing with finding the cardinality when you have several sets union together. So that's only two things left to do in sets, and then we're going to jump into logical operations, what's called predicate calculus, and truth tables for the next probably about two and a half days. Okay? But that's everything for now. I'll hang out if you guys got any questions, but I don't have anything else planned for today.